In this part, we're going to be putting together a lot of the um, things that we have talked about in the previous chapters, and especially kind of putting together like why did we even talk about some of those things, electron configuration or valence electrons, or where parts of the atom are located, and a lot of that is going to help form what we're going to be talking about, and we're really going to dive deep into chemical bonding and why atoms bond in the first place. So the main theme behind all of this is that atoms will either share or exchange electrons to form chemical bonds. And the real question behind this is why? Why do atoms bond? Why do they make compounds? And the simple answer is that it's more stable, which means they have less energy for them to bond. And let's take hydrogen, for example. So here on the right, we have two hydrogen atoms, and they each have their single electron. And at this point in the diagram here, we're going to assume they're a far distance apart. Now, as they get closer and closer together, so we're going to put these atoms closer and closer, and that's kind of notice this hill here. Eventually, they get to a point where they're at their lowest energy by taking these two electrons and sharing them together to make a bond. Now, you can kind of see, well, why is it going upwards again? Eventually, they get so close, the atoms will get so close that it's not favorable to be within that distance, and they actually repel each other. So there's this ideal like distance that the atoms will have and form a chemical bond between them. And that is lower in energy than them being apart. And one of the cool things about bonding is that the properties of the compounds can be completely different than their parts. So let's take, for example, sodium here. We can take sodium metal and react it with chlorine gas. Now, individually, sodium is a very, very reactive metal. And chlorine comes as a gas. It's a very, chlorine's also very reactive, very toxic as well. You react the two together and you make sodium chloride, which is just plain table salt. Not very reactive, very stable, and actually necessary for life. So you can kind of see here by bonding, not only is the resulting compound more stable, but has completely different properties than the atoms that form it. So just a kind of quick introduction about the types of chemical bonds that we're going to look at. Now, it's important again to look at the two parts um, of the periodic table. Remember, we kind of said that, well, all the metals were over here to the left of the staircase. Okay, minus hydrogen. Hydrogen is technically going to be part of the non-metals, which is on the right side of the staircase. Now, there are a couple of, or a series of atoms that I hadn't highlighted before, but I want to highlight now because the discussion might come up periodically. But there are some elements like boron, silicon, germanium, arsenic, antimony, and tellurium. Those ones that I highlighted in yellow, we refer to those as metalloids. The reason we call them that is because sometimes they have the properties of metals and sometimes they have the properties of nonmetals. Now let's just kind of review some things that we talked about in the past. So we've said that metals have loosely held electrons and nonmetals hold on tight to their electrons. And depending on whether the atoms you are combining are from one side of the periodic table or the other, dictates the type of bonding that they'll undergo. So if you have metals bonded together, so two metal atoms bonded together, that forms something called metallic bonding. If a metal bonds with a non-metal, there's actually a transfer of electrons. I want you to think about why there would be a transfer, and it's always going to be a transfer from the metal to the non-metal. Why would that be the case? I want you to think about that, and we'll dive deeper. And we refer to that as ionic bonding. And then when two non-metal atoms bond, this results in a sharing of electrons. This is called covalent bonding. So let's take a brief look at metallic bonding. And I'm not going to spend a lot of time on this, but as I said on the previous page, this is the bonding between two metal atoms. And we're not going to explore a whole lot of this in general chemistry. Think of metallic bonding like a sea of electrons. So the nuclei and the core electrons stay in place. And the valence electrons are free to move around and don't really belong to any certain nuclei. So let's kind of look at this diagram here. This shows sodium metal, and all of that dark blue area represents all that space where we say delocalized electrons can move. Now, delocalized, you're going to hear me use that term a whole lot when if you take organic chemistry, OChem from me. But that just basically means the electrons aren't stuck between two certain atoms. Those electrons can move all around this, well, not in the middle of the cations, but can move all around this blue area as they so choose. Now, if you think about that for a second, that gives metals one of their most notable properties, and that's the ability to conduct electricity. Why are metals so great at conducting electricity? Well, it's because they can allow electrons to move around very freely. And that's what electricity is just moving electrons. Now, as you can see, there's like a lot of empty space between the atoms as well. And that kind of gives metals, it's also another notable property. And that's its, we say malleability. Or we can shape it. It can be hammered into flat sheets or drawn into wires. Because there's so much space that allows the atoms to kind of compact together. Now, before I move on into any further types of bonding, I want to look at a special type of notation that we can use, and then I'm going to use quite frequently um, in describing some of our subsequent types of bonding. And this new type of symbol I want to look at are called Lewis symbols. Now, Lewis symbols show only valence electrons. Now, why do we care about valence electrons and not the core ones? Because as I've said before, those are the ones that get to do all the fun stuff. Those are the ones that are involved in chemical bonding. And so we use these Lewis symbols to show valence electrons, and electrons are represented by dots. Now think back to our periodic trends from our last unit. How can we quickly determine how many valence electrons an atom will have? Well, we're just looking at the rows. Remember, all the first column have one valence electrons or electron, two valence electrons, three valence electrons, four, five, six, seven, and then all the noble gases below helium have eight. Helium is kind of one of those weird ones I'll talk about in a little bit that only has two valence electrons. So how do we show these? Let's start with lithium. We just draw the chemical symbol, and then we put a single dot. It doesn't really matter if you put it at the top, bottom, left, or right. Just put a single dot somewhere. And then let's go to beryllium. I'm going to put two dots. Again, it doesn't matter where you put those in relationship to each other, just don't pair them. And I want you to think about why. Why do we not want to pair those or show those electrons paired up? And this goes back to electron configuration. Okay. Pairing up electrons results in less stability because they are closer together. So if we want to avoid pairing them up until we have to pair them up. So let's go over to boron. Boron has three valence electrons, so we show three dots. And then carbon has four. Again, I'm going to try to avoid pairing them up until I have to, like with nitrogen. Now I have to start pairing them up. Then oxygen, and then fluorine, and then finally neon with eight valence electrons. And again, I just want to highlight neon has that filled valence shell, or what we call an octet. And this kind of leads us to something we call the octet rule. And I put rule in quotes because it's more like guidelines because there are a lot of exceptions to the octet rule. But this basically, the octet rule dictates that a filled valence shell has eight electrons, and atoms will react. Again, I asked that question at the beginning of this lecture. Atoms will react because they want to have a filled valence shell. Now, already there are some exceptions to this octet rule. So exceptions like hydrogen and helium. Okay, think back to hydrogen here. Hydrogen is just 1s1. It can't gain, and it doesn't want to gain seven more electrons. But if it does gain one more, then it can be like helium, which is just 1s2. Now, yes, helium does not have eight valence electrons, but it is part of the noble gases because it still has a filled valence shell. So those are just a kind of a couple of other exceptions to the octet rule. But that's something you're going to hear me refer to a whole lot. And even in OCHEM, we're going to talk about the octet rule when it comes to bonding in chemical reactions.